Great news, everybody. It is springtime. And by springtime, I mean, of course, that wonderful time of the year when flowers bloom and we learn about springs. It also happens to be happening in October this year, but what can I say? Climate change. So, the first thing we're going to talk about with springtime is we're going to talk about Hooke's Law. Hooke's Law says that the force of a spring is going to be equal to K, which is our spring constant, times X. I'll write that over here real quick. Uh, F sub S is typically what we use for the spring force. And then K is our spring constant. We've talked about this already in a previous video when we were talking about spring energy. But again, the spring constant just describes how stiff or how bendy, yeah, that's the good science word, how stiff or how bendy the spring is. So if it's really, really hard to compress, it would have a very high spring constant. And if it's easy to move back and forth, it has a low spring constant. Finally, our last variable is x, and this is our change in length. Now, Hooke's law really describes the behavior of ideal springs, which is to say that any spring, if you stretch it too far or you stretch it too fast or stuff like that, this really breaks down. It doesn't work ideally. And even for springs that you kind of are doing a lot of this stuff with, you have to keep it between a pretty narrow range to really have the spring constant and such things really truly stay constant. But in this class, we're learning about the basics, the ideal cases. And in the ideal case, we're just going to use Hooke's law. It turns out that Hooke's law actually works just as well at a molecular scale when we're talking about the interactions between molecules. And so if you decide to go into chemistry, you'll actually see Hooke's law come up again as a discussion item for describing the elasticity of chemical bonds. But enough about that. Back on Hooke's law. Basically, what it says is that if a spring is very, very strong, it would require a lot of force to pull on it, and consequently, it would pull back very, very hard. But the most important thing, the part that students really get tripped up by, is they get tripped up by this part right here, the change in length part. Because we're not describing the length of the spring when we say X. We're describing how it changed from what I'm going to call the natural length. So I've drawn that natural length right here. Imagine that I have a spring kind of like sitting horizontally with a mass attached to it just for convenience sake. And if I just leave it alone, the natural length is where that spring wants to hang out. That's where there's no stretch, no compression. It's just where the spring rests at. So that's the natural length. And if we go to a stretch and I pull it a little bit more, that would be the distance x. And really, I could mathematically describe it. That would be something like whatever length 1 is minus the natural length is the measure of displacement. But you just want to pay attention to the values that you're given. Sometimes they'll give you problems that say a spring is 15 centimeters long, and then it gets stretched, and now it's 16 centimeters long. And the important information in there is not the 15 or the 16, it's the 1 centimeter that it was stretched. On that note, often springs, because springs aren't huge objects, having meter-long springs and stuff like that is kind of unrealistic, and I'm sure maybe exists somewhere in, like, I don't know, airplanes maybe. But for the most part, springs are pretty short, so we'll tend to do things in centimeters. So if you see something like 16 centimeters, just remember to move the decimal place over 2 spaces, and it would be 1.6 or 0.16 meters. Or just remember, we don't use centimeters, we use meters, and put that into the computer, ask it how to convert into meters, that kind of thing. So again, if we stretch a spring, this distance x is what we use in Hooke's law. Or if we compress it, again, this change in distance there, if it went from 15 centimeters, the natural rest length, the unstretched length, to 14, then we would just say, all right, in this case, ln minus L2 would be equal to x. So just look at the difference between it. The only other thing that I want to say on Hooke's law is the way that they teach us to use it in AP Physics 1 is they want you to use this specifically for the magnitude of the force. As in, they want you to mathematically figure out how strong the force is, but the direction is up to you. That's always true. There's a slightly different formula that has a negative sign built into it, but whether you put the negative sign in there or not, it's really up to the person to interpret what the sign means. So what I'm going to say with the direction of spring force is it always resists a change in length. So if you stretch it, it's going to be pulling the opposite direction. I pull it right, springs always pull left. I push it left, it's going to push right. If I switch those directions, it would still work. So that's what we need to know about Hooke's law and, in general, springs in situations that involve equilibrium. I'm going to write that as my last word on here: equilibrium. We can only in this class use Hooke's law in equilibrium situations. That's situations where it's at rest and the sum of the forces adds up to zero. Anything that involves motion, we can't use Hooke's law because it would be a variable force, which means we would end up with a variable acceleration, which means we can't use our kinematic equations. So if you're going to do anything with moving springs, you're going to do that with energy that we've already learned how to do. It's only when the system is in equilibrium that we start using Hooke's law. So I have two examples down at the bottom of the page. I have a spring with a spring constant of 100 Newton meters. That's the units of the spring constant. Hangs with a 5 kilogram mass attached. How far does the spring stretch at equilibrium? So as a quick sketch, I would have something like this. It's hanging. I know that I have a 5 kilogram mass on it. I know that my K is equal to 100. But when it comes time to draw my free body diagram, it's just going to look like this. It's going to be mg down and kx up. Again, if it says it's hanging, it's indicating that it's in equilibrium. It's not bouncing up and down. The acceleration is zero, which means mg equals kx, or I can solve it like I'm trying to solve for the stretch. Solve for x, that would be mg over k equals x. And I believe for this one, x works out to be the 0.5, 0.5 meters or 50 centimeters, which is kind of unrealistic for a spring. But there you go. That's how you solve the first one. The second one, this time we're solving for K, but it's the same general idea. This time it's being stretched horizontally. So we have some kind of force that's being applied to it, and then we're going to have the spring trying to pull itself back towards that equilibrium position. So once again, we are in equilibrium, so I can just say force applied equals kx, and then I can just solve for k because it would be equal to the force applied over x. And since the force applied is 250 and the change in length is 0.15, I think that k ends up being equal to roughly 1,666 newtons per meter or something like to that effect. I do have 3 6s in a row, so I do have to appropriately notate that. Okay, so there we go. Everything you need to know about springs. Thank you for watching.